Okay, we're back to finish up where we left off with V versus T graphs. I said there was two more conclusions. I think there's actually only one. So we looked at, so we said that one of the conclusions, here's how you tell the velocity on a velocity versus time graph. You simply look at the data points, you look at the y coordinates, the y variables. The slope tells you the acceleration. So in this case, we see that since the slope is negative, that means that the acceleration is also negative. We also see that the acceleration is constant, or because we see that there's a constant slope, since the slope has the same steepness throughout. So I'm just going to make a little note. So A is constant. Okay. Our last conclusion here has to do with the area under the curve. I said this time it was going to be meaningful. Notice that we found that the area is 250, and we found that it has units of meters. The area under the curve for a graph like this, on a V versus T graph, area under curve is equal to the object's displacement. Okay? The object in this case actually moved 250 meters. And that makes sense. It had a velocity the entire time. It started off at 40 meters per second, went down to 10 meters per second. Finding the area under the curve, believe it or not, actually tells you how far the object moved. Now you might be saying, well, hold on a sec. That doesn't make any sense. Okay? Why would the area tell you this information? That's totally out of left field. Well, let's think about it. Here's another way that you could find the area under the curve. Or here's another way you could find how far the object moved. We have these nice kinematics equations. Matter of fact, we looked at one the other day. Actually, many of these would work. So we know the acceleration. We know the initial and final velocities. And we could just say the initial position is 0. We can actually determine, using an equation, what the final position is. I'm going to do that right here. V squared equals V naught squared plus 2ax minus x naught. We're going to say that x naught is just 0. We know that the final speed, or the final velocity is 10 meters per second. That's going to get squared. Initial velocity is 40 meters per second. That's going to get squared plus 2 times the acceleration of negative 3 meters per second squared that we found times x. 10 squared is 100. 40 squared is 1600. So I'm going to have 100 equals 1600 minus 2 times negative 3 is 6 times x. I'm going to subtract the 1600 to the other side. So that's 100 minus 1600, negative 1500. Divide the negative 6 to the other side. Oop, forgot to be negative. 100 minus 1600 divided by 6 negative. Look at that. We find out that the final position is 250. And since we assumed that the initial position was 0, we said the final position is 250. That means the displacement, the difference between final position and initial position, was in fact 250 meters. So as weird as it sounds, on a V versus T graph, the area under the curve tells you the object's displacement over the period of time that it's being graphed for. I do just want to make one little note, though. There is something that you cannot tell from a V versus T graph. Without actually knowing x naught, cannot determine exact position. So we just assumed, and it didn't hurt us here because this wasn't really a situation that had a lot of detail going into it to begin with. We just assumed that the position was 0, that the initial position was 0. It could have been like 50. Okay, in which case the final position would have been 300. Still would have been the displacement itself is accurate, the displacement of 250 meters. All I'm saying is there might be certain circumstances where you need to know the exact position, not just how far it moved, and for that you would need to know the initial position. But anyways, the big takeaways here is that the slope on a velocity versus time graph tells us the acceleration, and the area under the curve on a velocity versus time graph tells us the object's displacement. Notice that this is different from a position versus time graph, okay? There were 4 conclusions here. The slope of position versus time told us velocity. The slope of velocity versus time tells us acceleration. The area under the curve was meaningless for position versus time, but it told us the object's displacement for velocity versus time. You need to know those facts like the back of your hand. The last type of graph that we're going to see in this course for kinematics, we're going to see tons and tons of graphs, is an acceleration versus time graph, A versus T. So I'm not even going to bother having us calculate the slopes here. If you look, you've got these data points up here. I'm just going to draw it in. So let's see, the data points, they're just like this up here. Then there's this big, huge jump. And now we have a different acceleration. Okay. Notice this time the acceleration actually does go down into the negatives below the x-axis. The x-axis is right here. Matter of fact, I'm going to dot that in right now. Right there. Okay. Now, I'm just going to tell you what the slopes are because they're pretty easy to deal with. And okay, so we're going to break this up into a couple different parts. The slope from 0 seconds to 8 seconds very clearly is 0. Anytime you see a flat horizontal line like that, that's a slope of 0. So the slope from 0 seconds to 8 seconds is 0. And the units of this time, since this is acceleration versus time, it's meters per second squared divided by another seconds. That's going to end up being meters per second cubed. Again, because if you take meters per second squared and divide by seconds, that's like saying meters per second squared times 1 over seconds, which gives you meters per second cubed. Okay? Now, there is a term for the, actually, do I want to talk about it right now? No, I'll wait. The slope from 8 seconds to 10 seconds is also 0. That's also a flat line, 0 meters per second cubed. What about the slope right at 8 seconds? Okay, vertical line. That is that's also kind of a weird one. So these are 0 slope. This is undefined. Now, would you encounter data like this in real life? No, you would never have an undefined slope. What you would have is a very, very steep slope, but that nonetheless, it doesn't go straight down. It would go very steeply down at an angle like this. But we're just making up some data here. This is like idealized data. Let's find the areas. I'm going to have, again, 2 areas here. I have this big, and remember, area is always the area between the line or lines of best fit and the x-axis. So our area is going to consist of these 2 blocks, this big one and this little small one. Here's the area of, and I'm going to call them just 1 and 2. Area of 1, this is a rectangle, so it's going to be base times height. The base is from 0 to 8 seconds, so base is 8 seconds long. And the height goes from 0 up to 6 meters per second squared. Now, a meter per second squared times a second, one set of those seconds are going to cancel out. We're going to end up with 48, 8 times 6, meters per second. For the area of number 2, we're going to have, again, base times height. The base this time is 2 seconds, from 8 to 10 seconds. Don't say it's 10, okay? The base here is only 2 seconds long. The height is 2, but it's a negative 2. That negative is important. 2 meters per second squared equals negative 4 meters per second. So the total area is A1 plus A2, which is 48 meters per second minus 4 meters per second, and that's 44 meters per second total. And that 44 is obviously positive. Let's answer our questions. Question number 1. Is the y variable positive or negative? In this case, the y variable is the acceleration, so we say A is positive from 0 to 8 seconds, then negative from 8 seconds to 10 seconds. Okay, that's how we would describe it. Question number 2. Is it increasing or decreasing? Okay, is the acceleration, the y variable, increasing or decreasing? So what I'll say here, I suppose, is, and again, this is equivalent to, is the slope positive or negative? It's almost easier to talk about the slope. I'm just going to say that A doesn't change. The acceleration doesn't change from 0 to 8 seconds, 0 seconds to 8 seconds, or 8 seconds to 10 seconds. But I'm just going to say it jumps at 8 seconds. Okay. Another way of saying that would be that the slope is not positive or negative, but the slope is 0 from 0 seconds to 8 seconds and from 8 seconds to 10 seconds, but at 8 seconds the slope is undefined. That's another way to say that. And then finally, is the slope getting steeper or not as steep or less steep? Is it getting more steep or less steep, or is it not changing? I'm just going to say the slope doesn't change because the slope is 0 except at 8 seconds. Now, our conclusions here. We're going to have a couple more conclusions. Okay? So this tells us essentially that we have an object that had a positive acceleration from 0 to 8 seconds, and then instantaneously that acceleration switched to being negative, a totally different value, and it's now negative. Okay? It instantaneously switched. That's what happened here. Let's see here. Okay. Conclusion number 1. To tell the and again, this is the kind of the common sense one, to tell the acceleration on an A versus T graph, read the Y coordinates. We can tell that the acceleration was positive 6 for the first 8 seconds, and then it was negative 2 for the last 2 seconds. Okay, pretty straightforward. This next conclusion will not come into play much, but it is a real thing that you could actually conceivably study. Notice that the slope, we found the slope was 0 except for at 8 seconds where it was undefined, and the slope had some weird units, meters per second cubed. We haven't talked about those units yet. Those are the units of a real quantity, and that quantity is called jerk. Slope of A versus T graph is what we call jerk. Jerk is simply the change in acceleration over time, but we rarely deal with that, okay? It's kind of fun to learn about. There is such a thing as change in jerk over time, and then a change in that over time. They're very humorously, these quantities called snap, crackle, and pop, like Rice Krispies, but no one really uses them, and, well, people use them, but we're not going to need them for any sort of application that we're doing, okay? But the slope is called the jerk, so little fun fact for you. And then, finally, area under curve for an A versus T graph. What is that? We found the total area under the curve was 44 meters per second, so clearly it has something to do with velocity. It is the change in velocity for the object over this time period. Change in velocity for the object over that time period. And it kind of makes sense. If you have an object that's accelerating at 6 meters per second, okay, for 8 seconds, think about this equation. This is right from the reference tables. Again, it's the very first equation. V equals V naught plus AT. Final velocity equals initial velocity plus acceleration times time. Let's assume that the initial velocity is 0 at this point. It doesn't really matter what we assume. But if we do V equals V naught plus AT, the acceleration is, let's say, 6 meters per second times 8 seconds. Okay, that would be what multiplying A and T does right here. It tells us that change in velocity. That's 48. Down here, we have an acceleration of -2 for 2 seconds. That's a change in velocity of -4. Add those together, we get a total change in velocity for the entire motion of positive 44 meters per second. So, the big thing for an A versus T graph is that the area under the curve tells you about the change in velocity, okay? We can tell the actual acceleration data points pretty easily, but we can also learn about the change in velocity. One note with this is that there is no way to tell, well, I guess what I'll call the actual position or velocity unless the initial position and the initial velocity are known. Okay, so you can say how much the velocity changed by. You could probably even also figure out how the displacement if you did a lot of math, but you can't tell exactly where something is unless you knew exactly where it started. Okay, so A versus T graphs, You probably see these, I don't want to say the least, but position and velocity graphs seem to come up a little bit more, but you still do need to know these basic facts for an A versus T graph. Let's look at something a little bit more complex, okay? A Regents student should be able to handle A versus T, V versus T, and X versus T graphs that we've done so far. They should know the basic facts. What we're going to practice now is reading something that's a little bit more complex. You'll notice that it's a position versus time graph, but it's still, the same principles are still going to apply, even though we've got a much different shape. Now, for some reason, I've kind of messed up the order of these questions. I definitely should have had like the bottom one first. So we're actually going to go back and start there. Approximately, so take a look at this. We have different time points, A, B, C, D, E, F, G. This is a position versus time graph. And what we see, so essentially what we're doing is we're mapping the motion of the object. The object didn't take a left turn and curve around and then go to the right and then go up and down. What we're seeing is the position of the object as it moved over time. Remember, this axis is the time axis. So this object seems like it stayed at 0 for a little bit of time. Then it sped up, it went in the positive direction. Okay, it kept going in the positive direction, but then it kind of topped out around like 12 or 13 or 14 or so. Stayed at 14 for a little bit. Then, what does this mean? It went backwards, went back through the origin, all the way into negative territory to about negative 21. Then it immediately moved forward past the origin again, and then once it got to about 19 or so, it stopped moving again. Okay, that's how you would read that. Okay, you're looking at data on the position of this object. So it's position versus time graph. Let's start with the questions. Approximately when did the object pass the origin? Remember, the origin is where x equals 0. Well, it's at the origin from A to B. When else did it pass the origin? When else did it cross back through that position of x equals 0? We can see that it happened 2 more times after it left, right here and right here. If I look at those time points, that one looks like it's pretty close to 15 seconds, but not quite, maybe like 14 seconds. Oh, I'm using my old answer key. Yeah, so about 14 seconds. And then this one looks like it happened sometime between 20 and 25 seconds. We'll call it 22 seconds. There we go. That's when the object was at the origin. Okay, how do we know where an object is on an x versus t graph? We simply look at the coordinates. It's at the origin at x equals 0, here, here, and here. During what intervals was the object stopped? What does stopped imply? It doesn't imply at the origin, okay? Clearly this object was not stopped at the origin. It's moving this entire time, okay? It doesn't like stop here and hang out for any length of time. It goes right through the origin, keeps going. When was the object stopped? Stopped implies that the speed is 0 meters per second. How do we know what the speed is on an x versus t graph? Well, we know that if we take the slope of the best fit line on an x versus t graph, that will help us understand what the average velocity is. And as a matter of fact, it's true that if you look at the slope at any point on an x versus t graph, that shows you what the speed is at that one particular point, okay? Looking at the slope at any point, especially if you have some complex shape like this, where there's not just a best fit line you can throw on there. Looking at the slope at any point on here will tell you the speed at that point. So if we want the speed to be 0, that means we need places where the slope is 0. Well, that occurred 3 different times. AB, CD, and FG. Those are all places where the slope is 0. Now, it's key that it says during what intervals was the object stopped, okay? Because you could make an argument that in order for the object to go from moving backwards at E to moving forward, or before E to moving forwards after E, it would have to stop. But E is just one point in time. It's not an interval. An interval is some length of time. E is literally an instant in time. All right, did the object have a greater speed during DE or EF? Remember what we just talked about. The slope of a graph, the slope of a position versus time graph, no matter if it's just a straight best fit line like we had on the front, or if we've got something a little bit more complex, the slope at a certain point, okay, the slope around a certain point on this trace of data tells you the speed. So if we want a greater speed, then that means we need a steeper slope. And I'm also going to make one more point here. Since we're talking about speed, that implies that we don't care which direction the object is moving in. Speed is simply, it's the scalar version of velocity. It doesn't matter which direction the object is moving in. Direction doesn't matter. If this had said velocity, this would be really easy because greatest velocity means it has to be moving in the positive direction. Okay, it has to have a positive velocity. That would be from E to F because that's where the slope is positive. Slope is the velocity. Therefore, the velocity must be positive there. That's the greatest. Since it's talking about greatest speed, however, we're just looking for the steepest part of the slope. Is that DE or EF? If we look, we can see that EF, that's pretty steep, but DE, you should be able to tell, is just a little bit steeper. You could actually do these calculations yourself if you want. E gets down to, let's see, about negative 21. D is, let's say, 14. So let's do negative 21 minus, I don't know, 14. Okay, so there's a change in speed of negative 35. This is at like 17. This is at like 12. So divided by 5 seconds. So the speed during this section was 7 meters per second. It just happens to be going backwards, so it's negative. Negative 21 all the way up to 19. So we do 19 minus negative 21 is 40. That's 17, and this is at like 27, we'll say, 26. So that's 9 seconds, so 40 divided by 9 seconds. That's just not as big of a speed, okay? You're comparing 7 to 4.44. The greatest speed, even though it's moving backwards, is from D to E. Okay? That's the part, out of those two intervals, that's the one with the greater, or the biggest, the steepest slope, even though it's sloping downwards. All right, now let's skip up to this first question. When did the object have a negative acceleration? Okay, now, x versus t graph, how do we look at acceleration? Okay, the slope tells us the velocity, so it's not just looking at the slope. It says on the front, and you can check this, that to make a description of the acceleration, you look for where the slope is changing, where the steepness is changing. So I would argue that the steepness is not changing anywhere except B to C. AB is a flat line, same steepness. CD is a flat line, same steepness. DE, it's not a flat line, but it's a straight line. The steepness doesn't change. E to F, steepness doesn't change. F to G, steepness doesn't change. Where's the only time where the object could have a negative acceleration? It's actually from B to C. Now, how do we know that it's a negative acceleration? Well, we see that the slope here is positive. Okay, it's a positive slope because the graph is trending upwards. So that means the velocity must be positive. But the velocity starts off very positive, the slope starts off very positive, and then kind of tapers off towards 0. Okay? Since the velocity is going towards being negative, or I like to say negative infinity, that's what a negative acceleration is. And we'll talk more about what a negative acceleration implies in class. The only time the object has a negative acceleration is during section or interval B to C. Now, I suppose you could also argue that it has a negative acceleration at point D or point F, but again, we're looking for intervals here. And then finally, during what intervals was the object speeding up? Speeding up implies acceleration. We already said the only interval here where the object is accelerating is B to C, but that had a negative acceleration and the velocity was positive. Okay? If the velocity is positive but the acceleration is negative, that doesn't imply speeding up. Think about what the object's doing here. It's moving really fast and then it kind of tops out around 14 meters. Okay? It stops at like 14 meters. That means the object slowed down. There is no interval here where the object was speeding up. The answer to that is none. Again, you could argue that B, D, B and D are points where the object speeds up, but we're looking for intervals. Okay, we'll get more practice with reading these more complicated graphs as we go through the course, okay, and as we go through this unit, really. But this is just a basics of looking at something a little bit more complex and using those basic questions that we've talked about, okay? What does what's happening with the y variable? Is it positive or negative? Is it increasing or decreasing? Is the slope getting steeper or not as steep? Those are tools that you need to apply to graphs like this. The last thing we're going to do, and we're going to practice this even more in the next set of videos, is look at some, what I would call these is like matched graphs, or like a set of graphs that all display the same motion but in different modes. You can see here that we have position versus time graphs, velocity versus time graphs, and acceleration versus time graphs. The goal here is to fill in if given this position versus time graph, what would the corresponding velocity versus time graph and acceleration versus time graphs look like? This is about as easy of a position versus time graph as you can get. Okay, it's an object. We look at it. We see, okay, the y variable, the position, is always positive. It starts at 0, I suppose, but it's always positive. Okay, it's always above the x-axis. It's increasing, which means an increasing slope, and the slope, it's the same steepness throughout. The slope doesn't really seem to change. So that gives us an idea of what's happening here. If we want to make the other graphs, we got to think about those conclusions. Okay. How do we know what the velocity is like? Well, we know from a position versus time graph that the velocity, that we can determine the velocity by looking at the slope. This is a positive slope clearly, and the slope is constant. It doesn't get steeper or less steep. That tells us, since the slope is positive and constant, that the velocity also has to be positive and constant. I would draw it like this. Could be higher, could be lower, as long as you draw something that doesn't change in velocity and is on the positive side of the graph. These two graphs show the same motion. This shows an object moving forward at a constant rate. So does this. It's just a different type of graph. For the acceleration versus time graph, we have the same sort of deal. This graph, remember, the velocity, so we look at this. This shows that the velocity is always positive. It shows that the velocity is not increasing or decreasing, which means that the slope is not increasing or decreasing. The slope is essentially 0. And that is the key for figuring out what the acceleration is going to look like. If the slope of this graph is 0, remember that the slope of a velocity versus time graph tells us the acceleration. If the slope is 0, the acceleration must be 0. So we would draw that in like this. That's 0 acceleration. We could have also gotten that back from our x versus t graph because we said to describe the acceleration, you look for how the slope changes. This slope doesn't change. That means there is no acceleration. That's why our acceleration looks like this. It's always good to describe what type of motion is being described here. So this could just be someone who is walking forward. Forward because we know the position's increasing at a constant velocity. Okay, that's all that is. And again, these three graphs all represent the same motion. I can get a motion sensor out and point it at someone, have them walk forward at a constant rate, and if I bring up a position versus time graph, a velocity versus time graph, and an acceleration versus time graph at the same time as they walk forward, all three of these graphs would get made. Just because they look different does not mean they tell you different information. The last graph on here that we're going to take a look at is a little trickier. Look at this acceleration, okay? We have a positive acceleration at first, then an immediate jump down to a negative acceleration. And it looks like these areas are approximately equal, and we're told assume that the initial position and the initial velocity are both 0. So I'm going to make little dots here. There we go. And there we go. This time we're going to work backwards. On an acceleration versus time graph, we know that we know it's a positive acceleration, then a negative acceleration. We also know that the area under an acceleration versus time graph tells us the change in velocity. What this tells me is that for the first half of this motion, there was a positive change in velocity because this area is above the x-axis. Positive change in velocity means that the velocity must be going up. Down here, the second half of the motion shows me a negative change in velocity. The velocity must be going down. Since these areas are equal, look what that comes out to. Since in the beginning the velocity is increasing going up, I'm going to have it go up to about here. And then we're going to lose that same exact amount of velocity. The graph ends up looking something like this. Okay? Positive acceleration, since it started at an initial velocity of 0, it gains some velocity. Then negative acceleration, same amount of area, means same loss in velocity that it gained. It's going to lose all that right back. It actually ends up, in this case, back at 0 for the final velocity. We can use the same sort of reasoning to figure out what happens to the position. Okay? This shows an increasing velocity. Okay? On an x versus t graph, the velocity is shown by the slope. If the velocity is increasing, that means the slope must be increasing up to this midpoint. That could look something like this. Okay, you gotta get good at drawing these, but that's an increasing velocity because it shows an increasing slope. And on a position versus time graph, slope tells us velocity. Then the velocity decreases, okay? So that means the slope here must decrease. And look how it decreases. It decreases back to 0. That means that this should flatten out, so that it looks something like this. If you're not quite getting this, okay, I recommend take another look at it, but also don't worry because we're going to do a lot of practice with these, okay? And again, these 3 graphs are all paired. They all show the same motion, but in different ways, okay? It's 3 different descriptions of the same motion. Matter of fact, that motion could be something like a car accelerating from rest, then stopping at a stop sign. So in other words, something that accelerates forward and then comes to a stop. Okay, that could be what's described here. Always be thinking of what sort of motion could be described. Okay, we see that the car increases velocity, then decreases velocity, but it still goes forward the entire time. On our next video, we're going to do a lot more practice with these. You'll get a lot better at it, I promise. Let me know if you have any questions. I'll talk to you later.